Hi everyone, I'm Professor Bergasser, and in this video we're going to be looking at the concepts of energy and work, specifically kinetic energy, the change of kinetic energy which gives rise to work, and energy in general as a topic of how we measure the motion or potential for motion for things out in nature. Now, we've already seen several different quantities for describing motion. These are our kinematic quantities, and so if we describe a path of an object as it travels through this two-dimensional space, we can describe the displacement of the object from one end of the path to the other. We can describe the velocity of the object as it passes a point, the amount of displacement per time. We can also describe how that velocity changes, and that's of course our acceleration. And all of these are different vector quantities that describe how an object moves and allows us to predict where the object is going to go as it progresses along its path. But all of these are vector quantities, and they're very specifically tied to the specific motion along a path. So one question you can ask, is there another quantity, an alternate quantity, that measures just the amount of motion? So that quantity is called energy, and it's a very common quantity. We talk about energy all the time in our sort of daily lives, but it's a physics quantity that describes either the motion of an object or the potential for motion, the quantity that allows motion to happen, that measures how much motion can possibly happen. Now, unlike some of our previous physical quantities, this quantity is not something that's just easily measurable. It's generally something we have to calculate. It's an abstract quantity. It's something that is a combination of things that we can measure, but in itself is not something that is directly measurable. However, it's also a fundamental quantity because, as we'll see, it's one of the quantities in nature that's conserved. In other words, it's something that is constant no matter what process goes along. The total amount of energy in a system in certain cases is completely constant. So it seems to be a very fundamental quantity in nature, but it's not necessarily one that we can directly measure. Now, there are many different forms of energy that exist in nature. We're going to be mostly focusing on the forms of energy that involve motion, and that's kinetic energy. But we see energy in all sorts of different systems and in different varieties. So you can have the energy of heat, which is thermal energy. The sun produces its luminous energy, radiant energy, that's the energy of light, by the process of converting mass into energy. So that's a mass energy that's converted into a thermal or radiative energy through the process of fusion. We see energy in chemical bonds. For example, the molecule ATP, which is our main energy storage molecule in our bodies. All of that energy is contained in the chemical bonds between the atoms in those molecules. And of course, we collect energy from the sun with solar panels and transmit it as electrical energy through our electrical grid. So there's lots of different forms of energy that are out there. And so one of the interesting aspects of physics is to understand how energy transforms through these different varieties and how we can actually measure that transformation. Now, it's important to remember that energy is present all the time in many different forms, even in the simplest systems. So I've shown here a model of the methane molecule, CH4. The gray spheres are represent the hydrogen atoms, and the black sphere in the middle represents the carbon atom in methane. And even in this very simple model, we have to deal with many different forms of energy. Certainly in the bonds that connect the carbon and the hydrogen together, these are examples of chemical energy. There's energy stored in the bonding force that's connecting those atoms together. The electrons around the hydrogen and carbon atoms have their own electrical energy, and that is an energy contained in the electric field that's produced by these electrons. We're going to talk more about that in our next physics class. When you go deeper into the atom has a nucleus at its core, and that nucleus is held together by nuclear energy. And that's also a source of fusion and fission reactions. So that's another form of energy contained in this particular molecule. Now, the molecule could be moving, and that's going to give us kinetic energy. It could also be randomly sort of shuffling around back and forth, and that random kinetic motion is also called thermal energy. That's where we get our concept of heat. And so that's actually a separate energy form than the sort of direct velocity of the molecule as it moves around, which is kinetic energy. And we can also look at light that is either being absorbed or emitted by the methane molecule. And of course, that light takes the form of radiative energy. So all of these energy forms are happening at the same time, even as something as simple as a molecule. And that means they're also happening all the time in our environment as well. Now, again, one of the aspects of energy that we really care about as physicists is how it's transformed and transferred across environments. And so if you have a form of energy, for example, electrical, in the case here of a light bulb, that electrical energy is ultimately responsible for the form of energy that we see, which is the radiative energy. So tracing how energy flows through systems and how it changes from different forms is a really key part of studying the physics of the world. So again, in this very simple example, if we have electrical energy moving through our wires, and that's literally the motion of the electrons through the electric field that's produced in the wire, that electrical energy through resistance in the copper coil or the tungsten coil is going to produce a thermal energy. It's converting electrical energy into heat. And that heat energy is then transformed into light through the process of blackbody emission. These are all aspects of how physics works at the microscopic level that we'll be talking about in later courses. But the important thing is to keep in mind that energy is this constant thing that's flowing through the system, changing its different modes, but nevertheless giving rise to different phenomena as it's moving through the system and transforming. Now, I mentioned that one of the fundamental aspects of energy is that in a system it can be a conserved quantity. And this is something that we're going to use very much in our solving several of our mechanics problems, looking at the total mechanical energy and how that total mechanical energy can be conserved if we have a closed environment. So I have a diagram of a closed environment here with a very complicated process that's happening inside of it. But as long as there's no energy being transferred across this boundary through light or sound or heat, then the energy contained inside this system is going to be the same energy no matter what's happening inside that system. So we can have a very complicated process and still know that the energy that we start off with is going to be the energy that we end up with, at least inside this system. That's a very powerful tool, but it's also a very powerful statement about how our universe works. Now let's get into the specifics of the energy of motion, and this gives rise to a quantity that we call kinetic energy. The kinetic energy of an object is just equal to 1/2 times its mass times its speed squared. And so an object that has twice as much mass of a second object is going to have twice the kinetic energy if they're moving at the same speed. And if you double the speed of an object, you're quadrupling its kinetic energy. Now notice that it depends on speed. These energy terms are all scalar terms. They don't have a direction associated with them. And so they don't depend on velocity. They depend actually on the speed squared. Now the expression we have here gives rise to a unit for energy, and that's going to be kilograms meters squared per second squared, just based on the mv squared terms that are in our expression. And we actually have a unit name for that called the joule, which is named after James Prescott Joule, who did a lot of research on energy, and in fact was the one to sort of promote energy as a way to really build our industrial society that we have today. Now, as I mentioned, it's a scalar quantity, so it has no direction. And because it depends on mass, which is always a positive number, and speed squared, which is always a positive number, kinetic energy can only be 0 or greater. You can't have negative kinetic energy. Now, we can quantify some examples of kinetic energy in the world around us. If we look at the fastest man alive, Usain Bolt, we can get his mass directly from Wikipedia. It's about 94 kilograms. And the fastest he's run is the 100-meter dash in about 9.6 seconds, which gives a speed of about 10 meters per second. And when you calculate the kinetic energy for that, you get a term of about 4,700 joules for his motion energy, his energy of running. Similarly, if we look at another sport, for example, fast-pitch softball, we can compute the energy of the ball itself. We can get the mass of that ball. It's about 170 grams. And the fastest sort of fast-pitch speeds are about 75 miles an hour, which we can convert back to our metric units. It's about 33 meters per second. And when you compute the energy for that, you get about 93 joules. So there's a lot less energy contained in a fast-pitch softball than there is in Usain Bolt, who's running the 100-meter dash. Of course, both of those are entirely dwarfed when we look at the energies of much larger moving objects. For example, the Earth itself. The Earth is in orbit around the Sun, so it's traveling around in a circle, and that circle has a total circumference of 2 pi times the orbital radius, which is 1 astronomical unit. And then the time it takes to travel in that speed is just the time of our year, 1 year. When you calculate those numbers out, you get about 3 times 10 to the 4 meters per second, or 30 kilometers per second, obviously much faster than Usain Bolt. And of course, the Earth has a much larger mass, and so we compute these numbers together, you get an incredibly large energy, about 3 times 10 to the 33 joules. So energy of kinetic energy happens on all sorts of different scales, and so it's important to make sure when you are comparing energies that you look very closely at the significant digits and the exponents so that you're not adding really small numbers to really, really large numbers. So once we have an expression for kinetic energy, of course, in physics we want to see how these terms change with respect to interactions with forces. And so to quantify the change in kinetic energy, we have a new term that we call work. So if we look at the change of kinetic energy, we're looking at the change of this 1/2 mv squared term. And of course, if we're looking at an object that doesn't change mass, what we're really looking at is how the change in kinetic energy translates into a change in the speed of an object. But we already know that the change of the velocity of an object depends on acceleration. So this change of kinetic energy is going to depend on the net acceleration of the object, and therefore depends on the net force. So there's a relationship between change in kinetic energy and net force, and that expression is called work, and it's just equal to the net force of an object, and that's a vector quantity, dot producted into the displacement of the object. So this is a vector operation, and we're taking two vectors that have directions, and we're coming up with a scalar quantity, and that of course has to be the dot product. Now this is an expression that we can use for work in the case where we have a force that doesn't depend on position. More generally, when we're actually computing the work, and again that applies in applied force and displacement, more generally when we're computing work for an arbitrary force that may depend on the position where you actually are in your sort of field that you're working with, in that case you have to take into account those variations. And we add up little bits of work as we move around our path, and that adding up little bits ends up to be an integral. And so the more general expression for work is the integral of the force dot the displacement element, the very small displacement element along our path. This particular integral is called a path integral, and it's something you actually have to compute as you walk around the path or as you move around the path that you're actually moving around, and what forces are acting in what direction as you're moving through this path. Now remember, we're using dot products, so we have to go back to our mathematics and recall what the way we compute dot product. We can either multiply the components of force and displacement, component by component, so the x position of force times the x displacement, and the y component of force times y displacement. Or we can use our geometric relation and note that the dot product gives us the magnitude of these vectors times the cosine of the angle between them. Now, this is a lot different than what we had with our kinematic quantities, where, for example, the velocity was in exactly the same direction as the displacement. We're actually now going to have to think a little bit more carefully about what is the direction that the force points and what is the direction that we're traveling in our displacement. So just as an example, if we've got a force that's acting at some angle theta with respect to our displacement, if they are generally along the same direction, then that's going to be the case where you have a net positive work, because the cosine of the angle that's less than 90 degrees is a number that's greater than 0. Right? It's going to be between 1 and 0. Now if you have the force acting in the opposite direction, not necessarily aligned, but in some direction that's sort of opposing the displacement, then that's something that's going to decrease the work, because now the angle is greater than 90, and that cosine of that angle is going to be a negative number. The most interesting case is if you have a force that is exactly 90 degrees from your displacement. In that case, that force does no work on the object at all. It does not change the speed of our object. And you can kind of see that because if we think about our Newtonian expressions, a force that's pointing perpendicular to one direction is not going to change the speed along that one direction. So if our displacement is entirely along one direction and our force is entirely perpendicular to that, then we're not going to have any change of our speed in the direction that we're moving. So this is where the dot product becomes really important when we're looking at the expression we have for work. Let's look at another example. One we've seen before is just sliding a box across a floor. And we can approach this from the same way that we approach our Newtonian problems, but we're going to focus a little bit in looking at what is the force that's actually doing the work on this object. Now, when we have an object like this, we're trying to draw a force diagram. We have to remember that this object has some weight, so it's going to have a weight force vector acting on it. And there's a contact surface at the bottom of the box, so we're going to have both a normal force acting on the box, and if we have any friction acting on it, we're going to have a friction force. And because we have a box that's sliding off to the side here, that friction force is going to be acting in the opposite direction. Now it's sliding friction, so it depends on the kinetic coefficient of friction times the normal force. Now let's look at each of these forces in turn and see which one is actually adding or subtracting kinetic energy from the box. And if we look at the weight term, in this case the weight is pointed in the perpendicular direction to our displacement, so it's producing no work. Gravity is not changing the kinetic energy of this box as it's sliding across the table. Similarly, the normal force is pointed perpendicular to the displacement, and therefore that's not producing any work. This is a common case. The normal force is what we call a constraint force. It's constraining where this box is allowed to slide, but it's not actually slowing or speeding up the box, and so it's not going to change the energy. So this is another term that's going to be zero work. So we're left with only one force that's actually doing work. This is our friction force. And because that friction force is pointing in the opposite direction of our displacement, that friction force is going to give us negative work, which means it's going to decrease the kinetic energy, which means it's going to decrease the speed, and that's exactly what we would have predicted for a box that's sliding across a table with friction. Let's look at a slightly more complicated example. If we have a satellite that's going around the Earth, then the force acting on that satellite is just the gravitational attraction between the satellite and the Earth, pulling them together, so pulling the satellite toward the Earth. In that case, we have, if it's moving in a perfectly circular orbit, the velocity vector, which is in green, is at 90 degrees with respect to the gravity force that's acting toward the center of the Earth. And remember, the velocity vector is in the same direction as our displacement. So no matter where we are in the circle, we're always going to have our velocity and our displacement vector at 90 degrees with respect to the force. And since that's always the case, the force dot displacement is always going to be zero. So in this case, gravity is not changing the energy, or at least the kinetic energy of the system. It's just redirecting the motion. So even though we have a net force acting on our satellite, because that net force is acting perpendicular to the motion, it doesn't change the kinetic energy, and it doesn't add or subtract any work to the satellite. And again, if it's moving in a circle, it's moving at constant speed. That's exactly what we'd expect if we just calculated what the kinetic energy is at these different times. So all of this together gives rise to what we call the work-energy theorem, and it's a way of relating the change in kinetic energy to the forces acting on the object, but in particular the forces acting along or against the direction of motion. And so in its general form, this is just equal to the difference between the final kinetic energy and the initial kinetic energy. That's going to be equal to the integral of the force over the path from its initial position to the final position. If, of course, that force is constant, this is just equal to the force dot, the total displacement. But remember that dot product because it's going to depend on the angle between the force and the displacement. Now, it turns out that this is completely equivalent to our Newtonian second law of physics, that the acceleration is equal to the force over mass, or mass times acceleration is equal to force. And you can actually derive the work-energy theorem directly from this Newtonian law. But the important thing is this is in a scalar form, and unlike acceleration, where we're often concerned about how that changes with time, with energy we're really interested in how forces change with position. So if you have a force that is variable with position or even constant, energy can be a very powerful way of solving problems and actually getting out what the motion of the object is without worrying about the time aspect of the force. So in a series of videos, you're going to be looking at ways in which we can solve various mechanics problems using an energy approach. And it's important to remember the steps that we could use to do that. Those steps are very similar to the approach we use for regular Newtonian mechanics problems. In fact, the first few are exactly identical. You always want to start by identifying what your knowns are and what you're looking for, and also figuring out what type of problem it is and making some predictions about the motion. And again, just like a Newtonian problem, we're going to break down our system into its moving components and create force diagrams for each of those components that are accurate and based on an inertial coordinate system. But at this point we diverge because now we can just identify some key times that we're interested in. So the initial and final time, maybe it's the initial conditions versus the point where something happens, like the ball reaches the top of its motion. And we want to write down the kinetic energies of the object or objects that we're looking at those initial times. Now sometimes we may not know all the quantities because those are the unknowns, but at least writing an expression for those kinetic energies will allow us to go to the next step, which is calculating the work done by forces acting on the object in the direction of motion, and then using our work-energy theorem to solve for any of the unknowns. And again, that work-energy theorem is really just the final kinetic energy is equal to the initial kinetic energy plus the work that's either added or subtracted from the object because of the forces acting. And of course, at the end, we want to make sure that we check our answers and test some extreme cases and make sure they match up with the predictions that we made just by thinking about the problem ahead of time. So you're going to get lots of opportunity to apply these steps for solving different problems. And remember, this is an alternative way of solving mechanics problems. Some problems will work much better with the energy approach. Some problems will work much better with the straight kinematic approach. And many problems will be solved by both ways, and it's a good way of checking your answers by making a solution using both of these approaches. So to summarize, energy is a new concept we're now introducing in our physics course, and it's a measure of motion, but it's actually an abstract measure of motion. And not only does it measure motion through kinetic energy, but also measures the potential for motion. We're going to see more of that potential for motion in our next videos. And energy is something that is much broader than just the motion of an object. It's something that is actually attached to all sorts of different physical processes, electricity, chemistry. All of these different forms have their own modes of energy, and those modes of energy can be transformed between electricity, motion, nuclear energy, through various physical processes. But an important thing is that energy is conserved, all of the energy is conserved in a closed system. And this allows us to solve for some very complicated situations by just looking at the energy alone. We've looked at kinetic energy as the energy of motion, and that's equal to 1/2 m times the speed squared. And the change in kinetic energy is related to the force through the work energy theorem. And that's equal to the dot product of the force with the displacement element, or through our path. Or if it's a constant force, it's just the force dot the total displacement. By computing this, we're able to solve many different problems in mechanics from these scalar quantities. And as we'll see, there'll be a very useful approach for a lot of range of complicated problems that would be very hard to solve from a Newtonian approach.